Alright, in our last video we talked about rotational inertia. So we were dealing with the I value for this equation. Today we're going to talk about how rotational inertia plays into the net torque provided on an object and then delivering a rotational acceleration to that. So we say sigma tau equals fish I. Fish being alpha, which is angular acceleration, and I being the rotational inertia of the object. The net torque is equal to the angular acceleration times the rotational inertia. Inertia is your resistance to a change in your motion. The net torque is what is trying to accelerate you. So the equation makes more sense written like this. Sigma tau over I is equal to alpha. So sigma tau is what is trying to start to spin you. Your rotational inertia is your resistance to that spin. And when you take one over the other, you get your actual outcome, which is your angular acceleration. So over here, this torque is force times distance. And then when you're looking at the rotational inertia, it's mr squared, so it's really the mass. Force over mass still gives you angular acceleration. So you're still taking the same ideas of Newton's second law, but you're applying them in a rotational manner. Let's just look at one simple equation and see what we get. So what is the net torque for a giant cheese wheel with a radius of 2 meters and a mass of 300 kilograms? That is being accelerated at 50 rads. All right, so sigma tau equals fish I. Alpha is 50 radians per second. And then over here, my rotational inertia is equal to, so it's a giant cheese wheel, so it's going to be 1/2 m r squared. So 2 squared becomes 4. 4 times 300 is 1200. Half of that is 600. And so we have 50 times 600 equals 30. 1, 2, 3 thousand. So the net torque is equal to 30,000 Newton meters. That would have to be applied in order to accelerate my giant cheese wheel at 50 radians per second squared. So we'll do a couple more examples in class, but that's our basic equation.